Hello guys, welcome to my YouTube channel. So today we are going to discuss lectures on bioplastics. Now bioplastics are mostly made up of polyhydroxyalkanoates. So polyhydroxyalkanoates are basically polyesters in nature which are produced by numerous microorganisms, specifically bacteria, and these polyhydroxyalkanoates can serve as a source of energy as well as a source of carbon also. Now, the general structure of polyhydroxyalkanoate is shown in the left hand side of the presentation. If the variable group, so here as you can see, this is a R group or a variable group. So if this R group is a methyl group, we called it as polyhydroxybutyrate, and if this is an ethyl group, we called it as polyhydroxyvalerate. Now let us see the synthesis of one such polyhydroxyalkanoate. For example, if the R group is a methyl group, how can this polyhydroxyalkanoate can be synthesized? Okay, so if the R group is a methyl group, I have already told you, so this is called as PHB or polyhydroxybutyrate. Now let us see how this PHB can be synthesized. So it starts with two molecules of acetyl CoA. As you can see here, this one molecule of acetyl CoA plus one molecule of acetyl CoA. So these two condenses in presence of the enzyme ketothiolase to form acetoacetyl CoA. Now the next step is the reduction of this acetoacetyl CoA by the enzyme acetoacetyl CoA reductase to form 3-hydroxybutyryl CoA. All right. Then this CoA molecule or coenzyme A molecule is released from this 3-hydroxybutyryl CoA by the action of this enzyme PHB synthase to form 3-hydroxybutyryl S synthase. Now in this way, PHB primers are added to form the final product polyhydroxybutyrate from 3-hydroxybutyryl S synthase. So basically, the starting product of PHB is two molecules of acetyl CoA which finally condenses, followed by series of reduction reaction and release of one molecule of coenzyme A to form polyhydroxybutyrate or PHB. Now this is how synthesis happens in case the R group is a methyl group. Okay, similarly we can also show that if the R group is an ethyl group, then synthesis can proceed in the same direction for polyhydroxyvalerate also. Now, E. coli is mostly used as a source of these polyhydroxyalkanoates because it has faster growth and gives better yields. Second point is that PHB can be produced from cheap carbon source like whey or hemicellulose by using recombinant E. coli cells. So this is also one of the most important advantages why E. coli can be used as a source of PHB or in general PHA, because it can be used on cheap carbon source, because the recombinant E. coli cells can be grown on these cheap carbon sources, and thereby we can get better yields of polyhydroxyalkanoates. How can we produce recombinant E. coli cells which express this PHB genes? So these PHB biosynthesis genes or PHA in general biosynthesis genes are introduced into the chromosomes of E. coli to generate the recombinant DNA molecules. Okay, and these recombinant DNA, when transcribed and translated, these produce the polyhydroxyalkanoates, PHA. All right, and then by growing these recombinant E. coli cells on cheap carbon sources, we can get ample amount of this polyhydroxyalkanoates. Absence of PHB depolymerase enzyme leads to the accumulation of high molecule of polyhydroxybutyrate. So this is also very important. PHB depolymerase enzyme is present in E. coli, which actually depolymerizes the polymer that is formed. I have shown you in the previous slide, I have shown you the synthetic pathway, where if you remember, here a number of PHB primers are added to this 3-hydroxybutyryl S synthase to form the final product of polyhydroxybutyrate. So for forming of this polymer, you need to have you need to stop the depolymerization activity. So it is because of that we need to inhibit this enzyme. This depolymerase enzyme needs to be inhibited so that this does not affect the polymerization of PHB. So this is very important criteria. When you are designing recombinant E. coli cells, you have to consider two things. First of all, you have to insert the necessary PHB genes, and second, you have to inhibit the PHB depolymerase activity. Otherwise, it will degrade the PHB polymer that will be produced. And the last point is that PHB molecules can be extracted by mild heat treatment at 40 degrees Celsius rather than chemical extraction techniques. So this is also one of the most advantages, that you do not have to use rigorous chemical extraction procedures. You can just use mild heat treatments and you can just extract PHB granules from the E. coli. Here I have shown an electron micrograph picture of how PHB granules look within E. coli cells when they are synthesized. So these are basically these granules that you see. These are basically PHB granules which have been synthesized within the bacterial cell. Okay. So what you have to do is you have to make recombinant E. coli cells. How do you make this recombinant E. coli cells? You make the recombinant DNA and insert it within the chromosome of E. coli, which when transcribed and translated produce these PHB granules. And second is you inhibit the PHB depolymerase enzyme. So these two things are necessary to do in order to get better yields of PHB, for example. Okay, so this enzyme needs to be inhibited. So in this way, actually what you do, if you realize these two are steps of genetic engineering. So in this way, you are basically making genetically engineered bioplastics or GEB. Okay, because you are using genetic engineering technique to make bioplastics, so this is called as genetically engineered bioplastics. So if you remember, here within the core structure, here PHB granules are produced, and within E. coli, here is the PHA polymerase enzyme resides, and here you have the PHA depolymerase activity. So to get better yields of PHA polyhydroxyalkanoates, the PHA polymerase activity needs to be upregulated and PHA depolymerase activity needs to be downregulated. So this is the basic structure, basic discussion on bioplastics.